Welcome, everybody, to our FDL Europe 2021 live showcase. It's fantastic to be here presenting this work to you. My name is James Parr. I'm the director of FDL Europe, and we're really excited to share this stuff with you. It's really kind of amazing that we get a chance to share this in this format, and we're looking forward to a great show. If you haven't joined one of our FDL presentations before, we are an artificial intelligence research organization. Our goal is to do open science and exploration for all humankind. And we're very lucky to be given challenges by our friends and colleagues at ESA that really matter, stuff that will hopefully make a difference to life on Earth. For this presentation and showcase today, I'm joined by my colleague, Chris Bridges. And we thought, well, we need someone who's sort of charming and sort of clever and knows about space. And I thought Chris could be the perfect person for this. So I wanted to welcome Chris and sort of, first of all, be nice to hear about you, but also I was wondering if you could also explain to the audience why this work is so interesting and why it matters.
Yeah, sure. Thank you very much, James. It's so important, really, because as we're sort of moving through sort of there's an explosion right now in data that's coming down from our satellites, but data generation kind of just everywhere. And what we're doing in FDL is seeing how we can then build new and bigger and better things, especially using the satellites that we work with. So yeah, I'm Chris Bridges. I'm a reader at Surrey Space Centre. And I mainly look at avionics, which is building computers for space. I'm working with operational data, and so working in the ground station. So I kind of have been working with FDL for about 3 years now, and with the fantastic team to then figure out then how we can then bring all of these new things from scientists into then real operational centers.
Thanks, Chris. So also joined by our partners here, and we couldn't do this work without our partners. The FDL is a public-private partnership. That means we're getting the best from academia and the private sector, commercial sector, and our space agency colleagues. We have Google Cloud, NVIDIA, Scan, Planet, Sense, D-Orbit, Airbus, Catapult, and Oxford. And you're going to hear from our colleagues later on today. But first of all, I mean, really, this couldn't be done without the visionary work at ESA. And I wanted to give the microphone to Pierre-Philippe Matou, who's going to introduce us from the ESA perspective.
Okay, many thanks, James. Can I just check that you can hear me?
Yep, loud and clear.
Okay, perfect. So I'm really honored to be here. I'm also very delighted because it has been a few years we have been collaborating together and with your team of excellence, actually. FDL has been for us a unique opportunity to really accelerate the use of AI for Earth observation. It was not a topic at the beginning of the story of FDL, so now it's almost the mainstream. And this year we have a very special topic on food security and machine learning on board, which is certainly the future of Earth observation and will help shape the new generation of mission. And if you can move slides. So this has been made possible through ESA, in fact, Earth observation programs, and in particular the PHI lab based in Italy. And this lab has the particularity that it's a kind of innovation lab within ESA. It has to scan the horizon and look for new technology. And AI was identified as one of the main impacts on the field of Earth observation due to the size of the data, the variety of the data, and the nature of machine learning, which is really scalable for this kind of problems. So this is really a new paradigm for the community. It changes the way we do the value chain of Earth observation. And we're also looking for new mechanisms. So in fact, FDL as a research sprint was a new mechanism for us to deliver results. And it has been doing consistently over the years with publication in top conferences. And at the beginning of the story, we had a lot of problems with the data, trying to get hold of the right data, to get the processing close to the data. But this year, I was really impressed by the ability of the team to really go straight into the the topic and deliver top results, even working remotely as they have been doing. So that's a bit the message I wanted to pass. It's a message of hope and opportunities, also of achievement. You managed to manage all these teams remotely across countries and with very complex topics and very high coaching. And I'm looking forward to the results today. I know these results will be used. They will be an uptake. There will be a follow-up. Possibly they will go to space. So I'm really looking forward to this. Thank you.
I also want to do a shout out. If you do go to ESA Fee Week, and hopefully in the future we'll be able to all be there in person. The Fee Lab and ESA Esrin has a fantastic interactive space. It's really worth a trip, and I'm sure absolutely a lot of learning opportunities for people interested in Earth observation. So the other, if you like, component to our formula is our relationship with Oxford. And really, I wanted to take a moment to introduce Professor Yaron Gal at Oxford Oatmeal. It's sort of hard to explain how important this relationship is. Oxford Computer Science is the world's top comp sci academic institution. They bring phenomenal experience and really allow us to achieve the world-class results that we do. So I wanted to give Yaron a quick moment just to say hi and perhaps talk about machine learning in space.
Cool. Can you hear me?
Yeah.
Nice. So yeah, so thank you very much for the introduction. So yeah, I'm Yaron Gal, Associate Professor in Machine Learning at the University of Oxford, and head of the Oxford Applied and Theoretical Machine Learning Group. We work both on developing new methodology in machine learning, developing new tools that could be used by practitioners, but also working with different practitioners in different fields, from astronomy to Earth observations to autonomous driving to medical domain, helping them take those machine learning tools and actually deploy them, build like real world, like use them for real world applications and deploy them in real world scenarios. I've been working with FDL and with ESA FDL since 2015, 14, 15. And I would encourage you, everyone watching, I would encourage you to go over the historical projects that we've done. There's lots of really amazing stuff from detecting informal settlements from satellite observation data to real-time producing real-time flood maps on the satellite itself in space, in orbit. Yeah, and anything else?
No, that's absolutely fine. And thanks so much for joining. And hopefully, Yaron, you can stick around for the panel as well, which leads me on to, if I can get the screen to go. Yeah. Really so thrilled that our colleagues from our partners can join today, and you'll get to meet them when we do our panel. Essentially, we've invited them to help interpret the work for the audience, and so this will be happening after the teams have presented their work in a few moments. So Yaron, you've just met, also joined by Chadi Rassi from INRIA, Michael Obersteiner from Oxford, Duncan Watson-Paris from Oxford, Sumit Ghosh from Scan Computers, and Sarah Cheeseborough from Catapult. And so they're going to feedback on the World Food Embeddings project. And then we also have our work looking at extreme event hotspots using machine learning on board. And the panel there is going to be Chedi again, Alison from NVIDIA, Massey from Google, Simon from Deorbit, and Kelsey from Planet. Hopefully Kelsey's not up yet. She's on the West Coast of the United States and we'll be getting a coffee. But actually, Massey, I'm very thrilled that you're here. And just wanted to sort of take a moment, and it's sort of quite hard to explain how phenomenal and what a transformative thing it is having Google in our partnership, because it allows our distributed team, which is spread all around Europe and some parts of the world too, to work together on these really complex machine learning pipelines. and also the data we're using is enormous. And I just wanted to put you on the spot, and I realized I didn't ask you to have anything prepared, but is there anything you wanted to talk about how you see machine learning informing science?
I mean, thanks so much, and it's a honor to be in this program and to represent Google Cloud in it. From Google Cloud, we're super excited by these results because they show not only the scientific advancement, but also the potential of applying AI to these fields. And very often, as you know, AI actually requires incredible amounts of compute. And the ability to have this compute being gathered very quickly from cloud becomes an essential component. So we're super happy to be that partner for FDL and to be able to represent that need. We're also super hyped up by the potential of this science to change both the world and the way in which we do exploration of the universe.
Awesome. Thanks, Massey. Thanks so much for getting up so early. So also, I want to make sure we said hello to Alison and Sumac from SCAN. And Alison, really the NVIDIA GPU has been the transformative technology for AI. And I just sort of wanted to ask you, again, putting you on the spot, what does this mean for you? Like what's the most exciting thing do you think people will see today?
So me or Sumit?
Oh, I think you go for
it. So it's just always such a pleasure to be involved in Frontier Development Lab. We're not called Frontier for any unusual reason, apart from it's about doing amazing things. Again, the fact that we've all had to do this remotely is incredible, but being able to harness GPUs, through Google Cloud is fantastic, but also having the support from SCAN so that we can have the DGX unit, the all-in-one with the CPUs and the storage, etc. That's, I believe they use the word, it's been the engine room of the sprint for the European teams, but then being able to burst out to Google Cloud and have the full gamut of Ampere is really wonderful to hear, but it's really about the results, and there is some incredible work that you're all about to witness now.
Thank you. So we're very close to letting the teams present what they've been working on. I just wanted to spend just a few more moments just explaining FDL for people who don't know who we are. Even though it's a research sprint that happens over the summer, this is the best time to get interdisciplinary people together. It actually is a year-long program. We also have a sister program with NASA and the SETI Institute in the United States. And I just wanted to perhaps ask Chris, what's the most fun part of this of FDL for you? When does it get exciting?
Yeah, well, it gets exciting, I think, and many of the team are probably going to hate me for saying this, but actually the last 2 weeks, I think, is the time where really you start to get your major results. You start refining on things to really push your objectives. And it's actually then when you start to then realize actually what it is and where it could work. Because even though that we might be focusing on much on the code, and I have to say, back to Massey and Alison as well, that the fact that they've been able to help us with all of these different tools, the important part will still be that we can go ahead, move forward with doing actual research, deploy it very quickly, and then be able to then push it then out into real world applications. So the last 2 weeks, I think where it all comes together, and now is really a celebration of that.
Perhaps you could help me. This isn't a great slide for this situation, sure. But I wanted to. Perhaps the message of the slide is the fact that we're growing a community, and one of the things which we like to say about AI is that actually teaching machines is it takes a village. Like programming machines is one thing, but actually teaching them is another. And so we're building a big community, and this slide sort of kind of represents the community that we're pulling together. We're very proud of our diversity numbers in terms of gender and ethnicity. Chris, you'll be able to talk to this, but that's not having nearly 40% women. I know we can still improve, but we really should be really proud of that, shouldn't we?
Oh, absolutely. You pick your study or your place. I mean, diversity is an important part of really any workplace. Not just on diversity of all the protected characteristics that we know and love, in the world, but also just for different schools of thought. In different places of the world, they will have different priorities. They'll have different ways of thinking about different problems. So diversity is especially important there.
Yeah. And really, that's kind of the secret. Like, we talk about the mystery of how to do AI, but diversity, interdisciplinarity, that's really the magic sauce. Over the last 6 years, we've been really starting to build out a portfolio of capacity. And really, this diagram was just to show that our sort of intention is to try and sort of take on big problems, big grand challenges, and atomize them into component bits. And you can see here that our sort of portfolio is growing, and then this year we're able to enrich this even more. So with that, I just wanted to sort of close by saying, if you are an AI researcher and you want to build on our work, and we're trying to make everything available, we're committed to reproducibility. This is our repo. It's called spaceml.org. On it, it's got all our enhanced data sets, data, notebooks, and MLOps for hopefully allowing you to run with these tools. And in the next few months or so, we'll be uploading all of the work you'll see today up to SpaceML. So with that set up, I really wanted to say thank you for everyone for joining, and for the teams to get ready. And we'll jump into our first presentation.
Hi, I'm Ilan Rajas, CEO of Scan Computers. What an absolute honor it is to be recording this message for FDL. As a bit of a background, Scan is a loyal NVIDIA partner, and we've seen over the years the huge technological advancements NVIDIA has made in parallelization. Of recent, the mass steps forward that we've seen in data. And in many ways, in doing so many of our talks, I often liken data to nuclear energy. And there's a universe of data that's being collated and created, and it's growing at an infinite rate. And combine onto that computational capabilities, especially with all the efforts that NVIDIA have put in over the years, and how efficient that computational capability has now become and being able to be distributed. It was an absolute pleasure to hear about the project from FDL, and we're absolutely stoked to be part of your initiative, and we'd love to donate and work with you in all the ways possible. The work done by NVIDIA, especially with the progression of GPU technology, especially with the new DGX A100 and Ampere processing that's coming out there, with a whole ecosystem of ingest with fast networks and storage, is so groundbreaking that it's well warranted to actually work with FDL to combine both these technologies. We look forward to working with you, and look forward to seeing some amazing results. Thank you.
World food embeddings. With greater famines and droughts around the world, and the ever-changing state of our climate, food scarcity is a very real and complex problem that faces a significant portion of the world's population. Machine learning applications with Earth observation data are limited by the availability of training labels. Training labels are typically spatio-temporal and correspond to events like forest fires or oil spills. Objects like ships, buildings or farms, or environmental indicators of interest such as vegetation health, crop yield or biodiversity markers. We asked the question, can we develop general purpose embeddings with time series of satellite imagery to build value-adding applications in support of the UN World Food Programme? It is, with this context, I'd like very much to introduce the World Food Embeddings team.
Hello, everyone. Thank you very much for joining us. I'm Francisco, and I'm very happy to be here as part of the World Food Embeddings team. First, let me introduce the team members. Our team leads are Freddy and Lucas. Our research advisors are Michael and Ian, and the researchers, Dolores, Raul, Julia, and myself. First, let me introduce you in the context of the problem. Right now, current reports say that over than 800 million people are suffering from food insecurity. And this has been worsened by climate extremes and the economic instability. So the World Food Programme and others are addressing these needs. And we have a vast amount of satellite imagery that has useful information that can help to address these problems. So the context is that from the habitable land, 50% is used for agriculture. And 82% of the supply, of the calorie supply, it comes from the plants. So, but also using the agriculture to change the lands. So the land use is changing. And when the land use change, it also affects the climate. So now the sequester of carbon, it is changing. And it is affecting the climate change. And this leads to increasing floods and droughts that are affecting the crops. So how can the artificial intelligence help to address these problems? Sorry, I'm having problems with the slides. So there it goes. So how can artificial intelligence help to address these problems? Well, we can create a map of the world by studying the crops from satellite imagery. But we need labels for that. For example, we need to know where the crops are, if there is maize or wheat, or if there is a crop or there is not a crop. And we have labels, but those labels are only in the global north. And we want to go at a global scale. We want to use models that can work at a global scale. And how can we do that without the labels? Well, that's a really hard problem to solve, because to have these labels, we have to go to the fields to annotate them. We cannot just look at a satellite image and say, okay, here there is some corn or some wheat. We have to go to the fields, and that's really costly. And there is no efficient and accurate automatic method to do that. So for example, in this image, can you see what is in here? It's really difficult. And not only that, also the global agricultural land, it's like 50 million kilometers square. So that's really big. And to store 1 single kilometer square, it takes like 5 gigabytes data. So that's a really huge amount of data. And the data extraction alone takes like weeks. And we need a lot of computer power to do that. So now I'm going to leave the floor to Julia, that she will explain more about how we use the satellite imagery to address these problems. Thank you very much.
Thank you very much, Fran. So as we just heard, we have an abundance of satellite imagery available. Our aims as a team, therefore, were to extract meaningful crop information based on satellite imagery with few or even no labels available. But how do we train our machine learning models without labels? We teach them the concept of similarity and contrast. Here you can see the same image twice. Within training, we expect our model to understand the similarity between those two pictures. We call this a positive pair, the raw image and the same image on the right, but slightly different. Here you can see a negative pair. Here we expect the model to understand the difference between those two images. And we can make this task increasingly difficult. Here you can see the same image, but cropped and in a different color. Through seeing many similar images and different images, our model can form an abstract understanding, and it learns to group the images through identifying the features that form a similar group. This way, we can create our own labels without having to rely on labels beforehand. I will now hand over to my colleague Raul, who will speak about the discoveries we made.
Thank you very much, Julia. Well, I want to show right now very briefly what are the things that we can discover with our models, and more importantly, who is the final user who may benefit from our models. So to jump straight into what we want to show, here we have a satellite image. This satellite image is from a single location. It looks like a mosaic because this is taken by as different satellite orbits, lightning conditions, and so on. It's a mosaic of different images in different times. But here you can see that there is a continuity. So it's actually the same physical place. There is a continuity of the roads, the fields, and so on. And it is what our models would output, starting from these images as input. You can see that there are patterns clearly emerging. There are colors. There are geometries of fields. There are many different things that are appearing here. How do we interpret these things? How do we make sense of these patterns? There are two things that are key to understand in this sense. One of them, it is that, well, we are using satellite Sentinel-2 data. Sentinel-2 is one of ESA's optical satellites. And the satellites are working on 11 bands. Usually the human eye can only see 3 bands, red, green, blue. And we are, just by the nature of the satellite, we are also being able to see details that normally a human eye would not be able to see. But more important than that, our models are capturing the time evolution of what we are looking at. So for instance, things having similar colors doesn't necessarily mean that they are visually similar, but it really means that they may have had a similar time evolution, like crops have a cycle. So maybe they have been harvested similarly, or they have been planted similarly, and so on. So this is what we are extracting from the actual data. We have developed a user interface for users to be able to interact with this knowledge. This is something that we have developed as part of our project to all the complexity, all the models, the data, and so on, to make it simple for users to be able to interact with it. So in this tool, as you can see, we can select a region of interest. We can zoom, of course. We can see the actual satellite data. This is the Sentinel-2 satellite data. This is, of course, RGB. One single 3 bands, one single point in time, and we can see little by little that our model is being overlaid. The results of our model are being overlaid on the satellite imagery, and then we can have a user. It could be like a farmer, it could be a policymaker, it could be a researcher that is saying, well, this region here, it looks weird because it should look like the regions around, it has the same properties. Why is it different in terms of time evolution and everything? So it clicks on the region, and of course we get like a digital signature of the region so that we can compare with other places, and they can say, well, this anomaly that I have found, where is located in my region, in my country? And here what you can see, it's very subtle. You see that there are many different points that have emerged. Those are places that are similar to what we have seen in terms of this digital signature that our model, this embedding that our model is producing. Yeah. So we expect that there may be many different kinds of situations and applications of what we are doing. We are, of course, still discovering these issues. And I'm going to hand on now to Dolores, who is going to be summarizing our results. Let me just, yeah.
Thank you, Raul. So as a summary of our work, we have built tools that allow to extract terabytes of Sentinel-2 images in minutes, creating new data sets of temporal images to enable new research. Also, as Raul was explaining, the self-supervised models we have trained allow to extract semantic information from these unlabeled images. And with this information, we can query where the crops are likely to be, helping the WFP optimize their data acquisition for crops. Using our models as a base to create crop maps where it wasn't possible before will help fight fear insecurity, decrease soil degradation, and create focused regional campaigns to support small landowners in less developed countries. And with this, I would like to thank everybody for joining us for this presentation.
Wonderful, wonderful stuff, everybody. And imagining like the huge applause around the world. So to help talk about this work, as mentioned, we invited our panel, a Y panel of specialists from our partner network. And really excited to just get some reflections from everybody. Hopefully you guys are getting your cameras on and microphones on, and we can spotlight you and bring everybody up just to talk about it. But sort of be nice to hear from you. This work is about scale, and it's about this kind of, if like, bottleneck that AI's had with labeling. I wondered if anybody wanted to jump in and just talk about what the implications are really for having this capacity, this capability.
I'll jump in if I may, James. I just want to say what fantastic work the team has done on this particularly challenging problem. You know, this is very complex data that they're looking to teach the algorithm to learn about and to understand without any guidance. And I think, particularly in the context of equality and this global kind of north-south divide, AI has been talked a lot about. There's been a lot of talk about how AI has kind of could increase inequality, and you know, you can see that with the labels here, right? That the countries which are able to invest in labeling the crops can perhaps get most out of the data. But this approach really allows any country to learn about their agriculture and to dig into the data in a completely agnostic way. They don't need to invest all that money up front. And I think that's a wonderful tool to be able to share with the world and with researchers who can now kind of build on that. So yeah, and I'm really excited by that.
Michael, that was your voice doing the intro at the beginning. This is your area of expertise. When you see tools like this, what does it mean for your work?
Yeah, well, first of all, I feel like I'm one of the old school guys now, who actually spent almost an entire career on exactly going out into the field, looking for the labels, work with crop models and see how you can actually synthesize this information between remote sensing with crop models. Never really properly worked. And this gives us really a new glimpse on how you could actually do things differently and basically turn the entire thing upside down, simply because we are entering a new era of, first of all, what the team really did, and this is really to be applauded, is as was mentioned already, this data preparation work that actually makes then also the data available more equitable to the global south. But then of course also the temporal aspect where we can now look very fast at change detection of the patterns that were detected, and this gives us absolutely new capabilities. And of course, currently we are not looking directly at an application, but very quickly you can actually think up and construct applications starting from, crop identification and even crop rotation identification, all the way to early warning systems of crop states, which for the World Food Programme is absolutely essential. Over.
Thanks, Michael. So Chetty and Sumak, you're machine learning people. When you see this sort of kind of engineering the team have done, why is that exciting for you?
Chetty, you want to go? Or?
No, go for it, Sumit. Please.
It's hard to do justice to the amount of work that has been done, and kind of, we've been following this through and what the things that be unsaid. The tools that were developed for this, to create this data, the volume of data that, they're talking about, manage it, and to do unsupervised learning in this sense. And they've created something called the array and so on for the, Google Cloud Platform. And I guess Massey is going to talk about it more. The amount of contribution that has just come out of this short kind of a project and kind of spurs on a lot of the machine learning kind of advances the field very, very quickly. And like any good research, this also spawns even better work. Like I think Raul was explaining, we look at, time-lapse, time series, the delta, how crops are changing, seasonality, and so on, how to understand that better, in short time, longer term changes, crop rotations, etc. And to have algorithms do that unsupervised, this is fantastic. And what's to come.
Thanks, Sumak. Chetty.
Yes, indeed. Yeah, first of all, I would like to congratulate the team for the work. And again, as Michael said, in fact, I remember 10 years ago when I started as a researcher at INRIA, one of the first projects we had was to go and prepare a few questionnaires to some of the farmers in Lorraine, which is a region in northeastern France. And the idea was to get the occupation of, of the land and understand basically how the crop, how they did their crop rotation. So it's quite incredible to see after 10 years how we went from, questionnaires now to have, satellite images that are being analyzed by a neural network and be able, in fact, without even labeling, so without even that kind of human expertise that can also introduce some errors, be able, in fact, to get meaningful knowledge and insights about it. So I'm really excited because this also opens up, a few interesting axes like, real-time detection, having some better understanding of how the crops rotate. And the interesting thing for a person also coming like me from the Middle East is also to see how this can be applied, for instance, for farmers in, the Nile River, like in the valleys around in Ethiopia, and in really interesting places where you really would really have a good edge if you could get this kind of knowledge and this kind of insight directly. So imagine if this kind of, algorithm can be, generated, and then you send the information directly to the farmers through the smartphones or through the phones directly, that would be incredible. So yeah, kudos for you guys. It was a really interesting project.
Sarah, you work at the Satellite Applications Catapult, so your specialism is the so what, like how do these things get applied? So when you were looking at this work, it'd be great to sort of get your sense of what it unlocks in terms of applications downstream.
Yeah, no, absolutely. The kind of interlock between sort of AI and machine learning and the more traditional sort of Earth observation side of things, it's been really exciting over the last few years. And this kind of work that's been happening here, especially with sort of embedding and unsupervised classification, there are lots of instances in which projects are there and there's the need for a certain application, such as this example of food security or food insecurity, and Earth observation data just can't be applied due to the lack of that training data. So having this unsupervised approach brings a whole lot of opportunities to certain communities, certain countries where that training data is certainly currently missing. And then as well as that, from kind of a broader perspective, it's sort of this is an example of one particular application on one particular type of data. So looking at agriculture with Sentinel-2, but it sort of gets you thinking, well, moving on how do we move to different sensors, and as well a whole host of different applications which this could be applied to as well. So it's a really important technology which is being unlocked here, which can go a lot broader as it continues to develop.
Thank you, Sarah, and thanks for our panel. I can sort of sense the conversation starting to sort of go to exciting places, and I feel bad having to stop at this point. But we're going to be joined by our ESA colleagues in a little bit. But first of all, I wanted to set the stage for our ML payloads team. And I believe we have a little film to set that up, and we'll give you the microphone in a moment.
In this challenge, the team looked to develop an opportunity for PhiSat-2 class microsats, testing how onboard ML can be used to reduce data transmission needs by enabling autonomous data selection of extreme events, or hotspots. Novelty detection is certainly a compelling problem for onboard ML. It has the potential to increase the value of downlinked data, and it is the premise for many use cases, such as disaster response, biology monitoring, or even continual learning, to cite a few. We at Google Cloud are very excited about the potential of machine learning payloads, and this application is an eye-opener to what's possible. I'd like to introduce you the Extreme Event Hotspots Using ML on Board Challenge.
Thanks very much, and hi everyone. We are the ML payload team. This is us, the researchers. So Vit, Anna, Danielle, and myself, James. Our mentors, Valentina, Gonzalo, and Valentina, and our advisors, Brad and Chris. I want to give a bit of the motivation for our project. So satellites are orbiting and continuously observing the Earth's surface, but they beam down images they capture without actually considering what is in those images. They don't know whether what they're looking at is something interesting or important. The scene might not have changed since the last time it was observed, and they beam it down even though there's no new information in that. And downlinking images comes with a cost, as we need to build more or higher capacity ground stations to receive those extra images. They also can't prioritize to get the interesting images down faster. So an intelligent satellite, which can interpret images, can boost data efficiency and decrease latency for those most pertinent images. But what makes a satellite image interesting? Well, for rapid events like fires, landslides, and floods, the satellite imagery can be used by first responders. Here, latency really matters. But there are many events we're interested in, and they come in all sorts of forms. They could be hurricane damage or oil spills, volcanic activity, deforestation, shifting drought conditions, all sorts. And these are all changes. That's what we're actually interested in from the satellite observations, is change. And if we can build a machine learning model which can recognize change, then a satellite could recognize all of these hotspots and more as being important. Currently, the machine learning models which run on board are supervised and only trained to spot one of these types. For example, the FDL 2019 project, World Floods, looks for floods. But in order to give the satellite more flexibility, more autonomy, we want something more generalized, something unsupervised, so it can capture all sorts of change. And that's what we've been building.
So let's have a look at one of those changes. These are two images, one before and one after an event. Here we can see the first change that is very clear. It is a flood event. It is in the middle of the screen. The river changes shape, changes color, becomes thicker. It's very visible. But there is another change. For example, there is snow which fell on the mountains. And this is another change which is very interesting because as well as the flood before, it adds information, meaningful information to the representation that we have of the scene. Yet, if we look at the same image now on a video, we can see that those are not the only changes in this environment. We can see, yes, the flood, the snow, but there are also a lot of minimum, very small nuances, very small changes that are made, for example, by the noise on the satellite sensor or lighting condition, atmospheric condition, and even clouds that do not bring much more information to the knowledge that we have of the environment. So we're not interested in those.
Thank you, Danielle. So let's look at the fundamental question, which is behind the problem, behind this challenge. And that is to answer how to compare two images to detect relevant change. So not to be kind of firing on the changes that Danielle was describing, so the small sort of just fluctuation between maybe sensory noise or maybe some small changes within the scene, natural changes, but how to trigger on something that is kind of substantial. Well, one way would be comparing between the kind of just the pixel space. So basically just between the pixels, and that would be kind of problematic because that would be sensitive to this kind of noise. In order to kind of fix that, we have been training a unsupervised variational autoencoder model, which is a machine learning model, which is tasked to take images from the sort of input side, encode them in this much smaller representation space that we call like bottleneck, and then using only information inside this bottleneck, again, reconstruct it on the sort of output side. And so by doing this, we are forcing this model to kind of throw away all the redundant information and maybe focus only on the important things which could describe the data. So it kind of learns how to understand this data. And how would we use this model to kind of maybe make some comparisons with change? Well, so instead of looking at the pixel values and comparing there, we could look at these encoded feature vectors, so these bottlenecks, and kind of look at the differences and distances in this latent space. And so what we hope and what we can see actually is that comparisons inside this latent space are more robust to this kind of noise. And let's see how this would be even used on a real world satellite. Well, we kind of hope that using this decision-making mechanism on board, we could make some intelligent choices already there. And so if a satellite seeing a new image of the same scene that it kind of saw before, if it is able to decide that there is something which has changed significantly, then it can decide to prioritize downlink of this information. And that could be perhaps alerting someone or just updating some information on this new content. If there is no relevant change, maybe it can still downlink it if there is enough bandwidth, but that is always limited. More or less, I mean, in addition, we actually also can make kind of more comparisons, not only with the previous state and the new state, but also with the whole memory of images. So as many images in the past as we can kind of save in theory. And using this latent representation, the advantage is that we have roughly 100 times smaller dimensionality of these vectors. So it is also much more easier to save many more images from that in this representation. And right now, let's look at how these models can actually do on some real world data.
Thank you, Vit. So these are the results of our model identifying an area of change, in this case occurring as a result of flooding. So on the left here, there are images from before and after the flood, and also a binary mask showing in yellow where the change has occurred. And we can actually see that quite obviously in this image where the river has turned brown as a result of the flooding. On the right are the results of our model, both for the VAE that Vit just described, and also a baseline constructed by taking the difference between images in pixel space. And we can see from this that both methods identify the regions of change. And more than that, the machine learning method using the VAE also gives much less noisy predictions. These are some examples of change detection using the VAE model for other types of change. Specifically here, we have fires, hurricanes, and landslides. So from left to right, this image shows examples of images before the event, examples after the event where you can see what changes have occurred, for example, the burn scar from the fire, a change mask showing ground truth of the change, and finally the predictions of our model. In all these cases, our VAE model is correctly identifying the regions of interesting changes. Finally, This table shows a summary of quantitative results using area under the precision recall curve as a metric, where higher numbers here are better. So here we compare the two autoencoder models, VAE and VAE100, to a cosine baseline in pixel space and also a random baseline corresponding to downlinking everything without any intelligent information extraction. For hurricanes, wildfires, and floods, the VAEs outperform the baselines, while for landslides, performance of the VAEs is roughly equivalent to the baselines, but with the added advantage that we're storing much smaller images due to that latent space compression. These results demonstrate that our unsupervised model can indeed detect interesting changes.
So let's summarize our achievements. First of all, we developed an unsupervised change detection pipeline that we call Raven using a variation autoencoder model, and we demonstrated that this can be used to detect new types of extreme events. In doing so, we also built a library and tools and a dataset that we aim to release to the community to foster the research in this field. And we can also see on the left panel that we actually run one of those models in the board that Chris is showing in the picture, which emulates the hardware that you can find on a real satellite. We'd like to leave you with this image. So you may have heard in the headlines what happens in Greece, where there are wildfires raging in, for example, here near Athens, the capital. And you can see from the image on the left, which is the image before, and the image in the center, which is the image after, that there is a huge burnt area. And on the rightmost image is our model predicting that change. We can clearly see the burnt area firing up in the top right, but there is also a small area on the bottom left, which is highlighted, which is not seen by hand, but it is actually a burnt area. This is the end of our presentation. We'd like to thank our advisors and mentors for the help and the whole FDL community and all our partners because they made it happen.
Wonderful, wonderful stuff, Payloads team. And also I wanted to congratulate you for sort of the different modes of work from software to hardware to labeling. You've really done some phenomenal stuff. So if we could invite our panel to jump on and turn your cameras on and microphones. It'd be nice to hear some thoughts and reflections on this work. And I can see Alison jumping in, and Massey, and hopefully Simon and Chetty. Excellent. Thanks so much for joining. So perhaps the first question, and Kelsey, welcome. Hope the coffee's kicking in. Really nice to see you. Thanks for joining. So really, question to the panel: why does this work matter? What should the takeaway be for the audience?
I can jump in if that's okay. So I think for me, I have kind of a personal connection for two reasons. The first being my job as a satellite operator. I operate the satellites at Planet and our Dove constellation. So anything that makes our satellites quote unquote smarter and gives them this sort of intelligence to make decisions as to what pictures are or are not important is just an incredible breakthrough. I mean, ground station resources are limited. Satellites can only communicate with the ground station when they can pass over that area of Earth. And so if we can have our satellites make these decisions as to what pictures contain information that's relevant, that would just be, groundbreaking, especially from a satellite operator perspective. Limiting any sort of human interaction just makes it better, especially for major constellations. And from a other personal perspective, I mean, I live in California, and wildfires, I've never experienced wildfires before until I moved to California, and the idea that we can use this sort of technology to reduce the latency and support first responders and determining, where the fires are moving and any sort of reduction in latency between identifying these sort of natural disasters, I think will be really life-saving ultimately.
Thanks, Kelsey. Massey, I saw you're nodding, and I don't know, why is this exciting from a machine learning perspective?
So I would say two things. The first one is that this is really kind of within a trend that is going on in AI. I mean, across areas, right? So you see actually kind of our phones and our consumer devices becoming more and more smart, and actually these AIs being applied there. And there are a lot of advantages of, like, in terms of latency, in terms of privacy, in terms of communication needs of those devices. So, I mean, it's time that we start moving this kind of intelligence also on our satellites. And if you look at it from a wider perspective, in a sense, we have done tremendous progress in the last 4 decades in terms of putting sensors in the sky. I mean, you can actually think about having our eyes in the sky now, collecting a huge amount of information. But our brains that parse all that information are always on Earth. And there is a bottleneck there. And I think actually the team had really hit the kind of crucial spot about enabling this kind of intelligence to also go up in the sky, live where the sensors are, and then be smart about what they communicate to all the rest of us. To Kelsey's point, I also live in California, and wildfire is a big problem here. But as the team kind of mentioned, it's flooding. It's just in general change that you want to know about. But change on Earth is all the time, and you want to know what is the change that really matters. And for that, you need a brain in the sky. So congratulations to the team. This is actually really impactful.
Chedi and Alison, same question to you. What, from a machine learning perspective, this is unsupervised learning again. What's the difference between where we have been for the last, if you like, 5 years of machine learning and what's happening now in unsupervised work?
Chedi, you can take that.
Go for it, Alison, if you prefer, but as you wish.
There is just a constantly evolving, fast pace, improvement over improvement over improvement. The various techniques that are coming into play with, generative imagery and creating and coupling with synthetic data, for example. There's so much actually happening. But from my point of view, intelligence in orbit, let's call them smart satellites. It will allow us, the autonomy of a satellite and huge constellations of satellites in a growing mesh right around the globe actually allows us to monitor all kinds of these very scary situations. And it's not just the obvious. ESA, Esrin, Pierre-Philippe et al. They put out this fantastic publication a couple of years ago on 99 different use cases. James mentioned a few of them, but one of the not so obvious is determining grassland v forest. Because our most crucial and time constrained problem now is acting on all of these cascading catastrophic problems, that we hear about. We know that forests, for example, help cool, but so far as permafrost, they actually warm and accelerate thawing. So there's a very, very urgent need to switch these massive areas, like Siberia to tundra, to grasslands. And we can easily do this with smart satellite constellations, with the mesh growing denser and denser as we put more satellites into orbit. And we can actually do the work, not just talk about it. And the embeddings work as well will actually speed things up, from the labeling point of view. But I think pulling in and coupling synthetic data along with real world, just like we do in the self-driving car scenarios, for example, it's a brave new world. And whether it's, Jetson or traditional FPGA that you're actually putting up into orbit, I'll stand by this statement to anyone. Waiting a few more years for for extensive testing for perfection is literally wasting precious time. And we have COTS, or commercial off-the-shelf hardware, on Mars right now. Qualcomm's Snapdragon and Ingenuity. It's actually operating on Mars, right now. So we need to act very, very quickly. And this work and the embedding work is really, really going to push actual action, which is what we need to do now, like by the end of the year, or early next year, not just talking about it. So congrats to all the teams. It's fantastic work.
I don't know what I can add over here, but just like maybe like a few sentences. But it's, for me, this project is more about one step towards getting, you know, some kind of fully autonomous, in fact, observation satellites. And this is important to say. And the important thing for me as a researcher in machine learning was to see that you guys, you worked on really interesting problems in terms of, you know, using a variational autoencoder, so adding a little bit of Bayesian log over here, and, you know, be able, in fact, to work on this idea of doing unsupervised learning or semi-supervised learning. These are really hot topics right now, because as you can imagine, we probably won't be able to label all the images that we get on different bands, on different, you know, positions and so on and so forth. So this is really a good approach, you know, towards what we really, you know, can dream of. And yeah, I mean, this was really a great work. Congrats.
Thank you. Simon, you're in the business of making intelligent, smart satellite constellations, those sort of things, and that Alison was talking about. You're actually doing it at D-Orbit. I was wondering if you wanted to have the closing word just to reflect on what you've seen.
Well, thank you, James. Yes, as you say, we're in the mode of helping to develop, to build these constellations with our sort of launch service. And we've had 3 missions in the last 9 months. The last one, of course, we're really happy to have the FDL 2019 Royal Floods application on board, which we're really looking forward to demonstrating the results of that in the next few weeks. And this work done this year, I think, is a sort of foundational capability that could be applied to all of the use cases and the benefits that we've been talked about so far, really enabling a capability which allows others to exploit all of these new technologies and the availability of new hardware in space, and kind of unlocking like an inherent value that's already there in many of the spacecraft that's already in orbit and will be launched in the next few years. So I think it's sort of the real-time responses to space data is starting another step in the evolution of how Earth observation is used for real daily use, which can benefit, you know, mankind in many ways.
Thank you, Simon. So again, I sort of sense there's like a lot of conversational branch possibilities here. And we're lucky that our colleagues at ESA are here to sort of reflect on this. So I wanted to just prepare them to get their cameras on, and hopefully, Chris, you can join me and just having a little reflection with ESA. But I wanted to thank the panel. We're going to play a little film just for 20 seconds, and we'll be right back to talk to our friends from FDL and ESOC. All right, well, welcome. So that was a really exciting series of presentations. And again, I wanted to congratulate the teams on the phenomenal achievement, not just in terms of impact, but the just incredible engineering behind the scenes. And I hesitate to say this, but I think in terms of engineering, I don't think we've seen this level at FDL before. And so I wanted to invite our colleagues from ESA, from the FDL, and also from Mission Operations in ESA ESOC, just to sort of talk about the work, but also to chat about AI in general. And Chris is here too, because he bridges both worlds. But really just to perhaps kick off and perhaps you could introduce yourselves, and then just sort of perhaps give us some reflections on what we've seen here today.
Good morning.
Yeah, Alex, you go.
I can start.
Yeah.
My name is Alessandro Donati. I'm working at the European Space Operations Center in Darmstadt, Germany. And in the last 20 years, I was leading, and I'm still leading a team of specialists with the objective of introducing artificial intelligence in operations for ENISA.
Thanks, Alex. Do you want to sort of reflect on the work? Do you want to sort of just get your first impressions?
Well, first I would say I have to share a vote of thanks to everybody, particularly the researchers, but also extended to the faculty and the other experts from ESA and outside, because in this time of big constraints, you still manage to do an excellent job and astonishing results, which honestly, they impress me quite a lot. For what concern the achievements, I would say this today, both activities, both projects are sort of can openers. So what you did, let's say you enable something that up to now was more related to be performed on ground. I know from my side, we were pioneers some 10 years ago on introducing novelty detection in mission operations on ground. And we got recognition for this leadership, but now it is really time to go beyond. And thanks to FDL and to the work that you're doing today, particularly, you demonstrated that we can have autonomous event detection on board. We can apply both to emergency, but also to other, let's say, non-emergency events, like some novel detection of a space event, or even for what concerns the health caring of the spacecraft when something is happening not expected. And what you're doing is, from an operation perspective, the first element of what I'm calling today autonomous event-driven operations. It's a sort of new avenue, which is in somehow one fundament for having much more autonomy on board in operations, so that you're not only detecting something first on board without interaction of ground, but if we manage to follow this, the first step that you have paved today with additional building blocks, then we can have what we call it full autonomous operation. So it's decision-making, planning, executing based on what you have detected. And this, I would say, will warm up and make it faster, because now it's time to do it. Even some other colleagues said, with taking the paradigm from the mobile phones, we also can see the spacecraft as a mobile phone on an orbit, and we can do much, much more right now. So I'm looking forward that this step that you did will be the kickoff of an adventure which will bring us an easy, much easier, faster, and high priority access to whatever is important being observed from outside the surface of this planet.
Thanks, Alex. Either Pierre-Philippe or Chris or Jose. And I noticed, Simone, I don't know if you want to join us. You're not on the, I don't know if we can bring you down to the panel.
Yeah, yes, I'm here.
Just to build on this idea of a can opener, because I think that's absolutely true. What the teams have built today is, two solutions, but with thousands of applications. So yeah, perhaps Pierre-Philippe, you want to build on that idea?
Yes, thanks, James. So I'm Pierre-Philippe Mathieu. I'm leading a team of researchers at ESA SRIN, also looking at how to put AI, but this time on Earth observation. So in full complement with what Alessandro was telling before. So reflection, that's really deep on a Friday afternoon, but what I've noticed over the years, and since I know FDL for a few years, is first that the brain is changing, because machine learning in itself is a new paradigm. And I've seen it coming to our field, in particular over the last 5 years, like a tsunami. And you see this in the number of publications. So this ability of creating software when you don't understand fully the problem and feeding on the data, which in our field is big data, is really disruptive for our field in general. And this has been shown already by FDL over the last few years, mainly through supervised learning. So this year is the year of self-supervised learning, and this is really the new frontier, where the machine are able to understand by themselves, and it's a bit scary in a sense. So this alone on ground is already an achievement and opens totally new way to do Earth observation, in particular has a hybrid scheme with supervised and non-supervised. But which is even more exciting, and that was pointed by Massi before, is that the eyes are in space and the brain is on Earth, but now there might be a convergence of both through new hardware. And if the brain is closer to the eye, this will change everything. In terms of autonomy, in terms of commercial business, this was alluded by D-Orbit. There is a gap of latency there, and there might be a big business which is still hidden today. But when you will get environmental information on your mobile phone in real time of things happening around you, I can tell you this will be transformative. So what we have seen today is really the building blocks of this. In fact, all the elements are there, the software, the hardware. We just need the will. I think we have it in the team, but not everywhere. So we need you to spread the word. And we have this beautiful diversity, both in the team, in the network of FDL, in the variety of actors concerned by this, from the hardware guys to the software to the application people. I mean, this is a full biodiversity at work here. And this is super exciting. So I wanted to congratulate you, your team, but also the FDL teams themselves. I think what I've seen this year is the best, how can I say? It's one of the best year. I don't know if it's because it was remote, but the capability to deliver in such a small time, but with real prototypes is really truly amazing, because the previous years, we had problems with data augmentation. And this year, the whole chain is there. And again, congratulations.
Thanks, Pierre-Philippe. We're just whispering that it might be better than other years, not saying explicitly. But Chris, you have your hand up.
Always getting better, but the standards are always higher. That's what I meant.
Yeah. And following on from that, a big part that, Alessandro and Pierre-Philippe had mentioned is, of course, the data sets. And I think what we're becoming a lot more now as we do this year on year is becoming more savvy to that data sets are important. You can't do any of this without good data sets. So the stuff that we've done either with Simone or Pierre-Philippe, it does come down to those things. And I guess one of the questions I might perhaps ask you guys as well is, what do you think the big barriers are to using this sort of black box type of autonomy? In sort of the industrial space world I come from, if you're having a black box of weights that to sit in code somewhere usually makes people, how do I put it, slightly more nervous, okay, in understanding now that these things can make decisions on their own. And so it becomes very hard to plan power budgets and data budgets. How do we think we can resolve that? Or do we just have to just take the leap and in that step function and moving to autonomy?
If I can say something, that was actually what I was thinking. Now things start to be serious. Now we are in a position where we can, when you have these tools that are starting to take responsibilities on board. Okay, so when you start to take responsibility, there is, of course, a problem of verification, validation, a problem for explainability. And we need to redefine in space, first of all, you can't straightforwardly validate these technologies like it was done in the past with other types of technologies. But at the same time, you need this validation. So the key point here is probably to redefine the concept of validation. How do you validate? Because you cannot skip this step and you cannot apply straightforward what you have. So explainability, another point that is very important here sooner or later, because now, you know, they take decisions and they do things. And you cannot recover from that, because once, for instance, in this application we have seen, they decide to discard an image, this image just gone. You can do nothing. So that's a very good point. That's probably is going to be the difference with the trademarking factor that can actually really make the difference for these technologies to go into the baseline in the future. Because spot applications are always possible, but to really trust these people, especially out of the loop of people who are experts, because we have trouble in understanding some things here, and we trust these technologies because we do these things. Imagine people that are completely out of this loop.
Agreed. Jose.
I'd like to mention a bit on the impact of this project that I see. First, well, from the audience, I don't know how much familiar they are with machine learning, just to highlight that doing unsupervised learning is a lot harder than if you have labels. So I congratulate the team, just to show the appreciation of the people who don't know this, also notice that it's much harder. And for the impact in operations and in science, what I see more is that this will be more valuable when you have less bandwidth, or when you have some restriction. So for instance, for big satellites where you don't have such of a problem, maybe it's less interesting. But for CubeSat or constellation of CubeSat, where you're limited by power, this having change detection and prioritize the payload images that you get is a very cost, or let's say the return of investment will be much more, because you get the actual interesting science for the limited bandwidth you have, which is possibly limited by power. And the example was on Earth, but nothing prevents that the same thing happen with Mars or other planets where you have even more reduced bandwidth. So I see plenty of application, and it's a very high impact on this reprioritization. I mean, as you were discussing, I concur with you that it will be an issue, to validate and explainable AI and so. But I will say that for this particular problem is maybe not a big deal, in the sense that you cannot send all the pictures that you wanted anyhow. So if you have a better way to do it, if you compare this with the alternative, it's not much better anyhow. So yes, I agree, not to be validated, you have to have confidence that you are doing a good prioritization. But if one of them you get it wrong, it's also nothing very wrong happen.
Thank you. So I just wanted to, again, just thanks to the ESA team, and also just, it is a sleeves rolled up. That the ESA team have been very, very engaged in helping the teams, and of course we couldn't do it without you. So we're very grateful. But this is also a reminder that FDL is about collaboration, it's about interdisciplinarity, and it's about a culture of collaboration. So to celebrate that, we have this, we call them awards, but it's not really a competition. Certainly not, it's not really like that with FDL, but we do like to celebrate the work in a fun, engaging way. And this is really our wrap up for our presentation today. So hopefully, Alison, I'd like you to join me on the stage, and you can be help with the envelope, and we'll just get the slideshow up again here, and we'll go and talk about just to celebrate the work of the teams. So hopefully, Alison, are you on stage?
I'm here.
Brilliant, excellent. All right, so this is our collaboration awards, and again, just to repeat, this is just celebrating really the culture of collaboration that the teams have created. And so we have a few awards. The first one is in celebration of the heroic comeback, which is represented here by the Apollo 13. And this is true of anything which is new. Like anything when you're doing new work, there's always going to be a little bit of a journey that people go on. And so essentially we say here, the heroic comeback is an acknowledgement that when discovering something uniquely new, you have to first fail. But that's only one half of the story. Simply failing isn't enough. Getting back up, learning and evolving and trying is how legends are made. So, Alison, would you like to tell us about the winner of the Heroic Comeback Award?
Yeah, so there is one particular individual who definitely embodied this spirit. They're on the World Food Embeddings team. This one individual in particular worked through external challenges, but also internal processes and issues, and in doing so, really helped the team's reproducibility. So drum roll, the Heroic Comeback 2021 award goes to Julia Gottfriedson.
Hey, virtual claps, Julia. Congratulations and thank you for working so hard. But of course, really, we wanted to acknowledge the team as well, because you've had a brilliant supportive environment. It was great to see how you worked through FDL this year. So the next one is the Collaborative Spirit Award. And this is two astronauts sort of helping lift something, I guess that's what this is. And so the Collaborative Spirit Award is the representation of FDL's beating heart, interdisciplinary research. It supports the idea that to achieve great things, 2 or 20 minds are better than one, and the exchange of knowledge is key. So, Alison, do you want to open the envelope?
Yeah, actually for this award, there were a few honourable mentions, particularly Dolores Garcia and the World Food Embeddings team, who've actually just been standout collaborators. And in any other year, they would have won, but in 2021, in recognition of their professionalism, their active listening, and proactive helping, mode switching from labeling in QGIS, model optimization to hardware, and just sheer consistency. The Collaborative Spirit 2021 award, drum roll, goes to ML Payloads.
Yay! Again, very weird without a kind of round of applause, but imagine that it's people are clapping. Excellent. Thank you so much, Alison. All right. So most dramatic pivot. So this is obviously this is an asteroid which is being redirected. This is what this award is showing. And so pivoting is the action taken when new opportunities arise unexpectedly. Sometimes this means starting completely from scratch after what a commitment is already put into one area. The most dramatic pivot award represents these changes in direction, at times unwanted, but always necessary. So, Alison, do you want to open the envelope?
Yeah, I mean, since day one, FDL is just a hugely dynamic process, but sometimes the FDL teams are handed problems with very clear boundaries. Other times they really have to find their own way, fishing around in the dark. But during this year's FDL, one team pivoted from trying to solve a very discrete challenge to creating a toolbox that will definitely enable others to solve many, many, many more problems. So the Dramatic Pivot 2021 award definitely goes to World Food Embeddings.
Yay! Again, well done, everybody. And we'll. I should have mentioned that these awards do exist, and we'll give you a 3D printed version of it. But there's only one per team, so you'll have to probably figure out how to share it. Or perhaps we could print some small ones for you. All right. So the next award, most useful contribution. So what defines contribution? Machine learning, it's hard to spot. It really is. The thankless task of data preparation on behalf of the community, or the application of a freshly minted ML methodology to a new domain. In some instances, it's something that widens our perception of what's possible. The most useful contribution can be any and all of these things, as long as the ultimate beneficiary is for all humankind. So, Alison.
Yeah, definitely in machine learning, data prep is 90, perhaps more % of the work. So try to imagine the utility of a tool that can access terabytes of imagery in minutes and massively parallelize experimentation. A data prep pipeline that will undoubtedly be used by FDL and many, many others. So for the development of the World Food Launcher, the most useful contribution 2021 award, of course, goes to Raul Ramos and Francisco Dor.
Well done. And again, I just sort of, even though we're symbolically highlighting Raul and Francisco, this team was absolutely in lockstep. And Dolo, I just wanted to, and Julia, you should really be recipients of this as well. And this is perhaps the fault of the system, but really wonderful work, and we're thrilled with what you guys have done, but also just how hard you worked. Like, it is quite extraordinary what you achieved in the time. So the next award, the Night Lab Award, this is actually a new award for this year. And because of our virtual status and our distribution around the world, we wanted to create a special mention award for team members that went above and beyond, working both day and night in time zones spread around the world to make things work. So Alison, do you want to open the Night Lab Award?
Yeah, so in a year where, in yet another year, where there's been such an astonishing work ethic and people working over multiple time zones, there was one standout night owl who, even though she was in Tasmania, never missed a beat. So the Night Lab 2021 award definitely goes to Anna Bourne.
Well done, Anna. And we did hear that there was absolutely no evidence that you were working through the night, which I have to say is pretty incredible. So thank you so much. All right, so so we're going to our final award, which is the Steely-Eyed Operator, which is really in celebration of the ability to keep calm in the heat of the moment. And we give this to our faculty. And this is named after the flight of Apollo 12, I think, which was hit by a bolt of lightning in the mission control. They decided to keep on going despite sort of across the board sort of stalling of all the equipment. But they decided that it was okay to keep going. And this is where we get the phrase steely-eyed missile man. But we have this award, the Steely-Eyed Operator. And in every FDL project, there's a moment where everything can go wrong. This is the implicit contract of high-risk, high-reward research. If you don't go through this, then your work isn't new. Remaining clear-eyed and headed in this moment is a rare quality, and without it, FDL wouldn't deliver. The steely-eyed operator acknowledges the efforts of a faculty member who's regularly been the calm voice in the storm. So Alison, do you want to reveal?
Yeah, continuing on from that, but one of the things that FDL prides itself on is the very high project success rate. Machine learning is fiendishly difficult, and many ML projects in industry, in fact, fail fast. So what is the secret? It's very complicated, but two of our faculty members know all about this. For 3 FDLs in a row, they both have consistently delivered genuinely breakthrough work, and are both generous, hardworking, and always a pleasure to work with. We are humbled, we are in awe, and forever appreciative. So the Steely-Eyed Operator 2021 award goes to Valentina Zantadeshi and Freddie Collective.
Thank you. So I cannot reiterate how yes, just humbled and in awe we are of what you do. The work you've done over the last 3 years is phenomenal, and we're very, very grateful. I just wanted to again just sort of say thank you to our FDL family and community. Thank you for everyone watching. It's been really a thrill to share this work with you. And Chris, I don't know if you've got any sort of closing thoughts or reflections, or this is going to be a weird thing where we turn the camera off and suddenly it's going to be like tumbleweeds, and after working so hard, it's going to be a strange moment. But Chris, I don't know if you wanted to close off with some thoughts.
Yeah, I think there'll be a time of sort of collection where you'll have the sort of weekend, maybe back again, to figure out really what you were doing. And hopefully really though, FDL's not only just widened perhaps your eyes to networks and to techniques and to new data sets or new ways of doing things, but also the fact that actually this community is going to keep on going, and that actually being part of this is really a lifelong type of thing. Hopefully you will have met people that you'll keep in contact with, and you'll keep in contact with us too. I know certainly in one of the teams we'll be continuing to work on these applications as well after this, actually just because actually it's fun and it's good science and it's exciting. And I think with that, I'll hand back over to you, James.
All right. Well, thanks everybody. Thanks everyone at home for watching. We say ad astra at the end of all of our emails and everything. And of course, couldn't do it without our partners. We're very, very grateful, and of course the hard work of the researchers and faculty. So with that, we'll let you enjoy the rest of your Friday, wherever you are in the world, and hopefully we'll see you next time.